recording now. So starting in on the section on Stokes' theorem. So for Stokes' theorem, you've got some kind of surface. Let me try this again. Alright, so you've got a picture of a surface kind of like that, and you are oriented positively. Now, what does that mean? So the boundary curve of the surface is here. And if you take your right hand and you slide your fingers in the direction of the boundary curve, your thumb should point in the direction of the surface. Okay, so the orientation of the surface and the orientation of the boundary curve are as such. And this is a two-sided surface, right? Described in the video, a one-sided surface. Essentially only one example of that in 3 dimensions. That's the Moebius band. There are actually other examples, but they're just Moebius bands hooked together in a certain way. Okay. And in this case, the line integral over C of f dot dr, or ds, dr, whatever, is equal to the surface integral over s curl of f dot ds. So the line integral is equal to the vector flux integral of the curl of the field across that surface. So it's easy to apply Stokes' theorem in that direction. So calculate the line integral via calculating the surface integral. It's not so easy to calculate it in this direction, because here you'd be starting with some field G, and over here you'd have some field F, like the uncurl of G. So, the curl of the uncurl of G would give you G back, but uncurling a vector field is hard. I mean, it can be done. There are ways of doing it, but we don't cover it in this class. Dr. Fang actually knows a lot about this kind of stuff. Dr. Wei Fu Fang, I don't know if any of you know him. He's in the department. Okay. So, number 329. And that's the meaning of curl, by the way. I mean, there's all kinds of, attempts to give meaning to curl outside of Stokes' theorem. So this is Stokes' theorem, sometimes just called the curl theorem, and it's essentially that's the meaning of the curl, is that it's the vector field that satisfies this. So 329. F is this, S is the upper hemisphere of that. Without using Stokes' theorem, calculate directly both the flux over the given surface and the, we're not doing the circulation integral around its boundary. Circulation integral? No, the flux integral and the circulation without using Stokes' theorem. Well, you got to do one or the other. I mean, you can calculate the line integral directly. So, for example, in number 329, you have vector field F is z 2x 3y And S is the upwardly oriented hemisphere of radius 3. So, get this one. Why is it so hard to draw suddenly? Okay, so that's the hemisphere of size 3, of radius 3, excuse me. So that's 3, 3, and 3 on the z-axis, x and y-axis. And it's upwardly oriented. So calculate, and then C, of course, is the orientation of the boundary, like that. And what is C? C is just the circle of radius 3. Right? So C is the boundary circle, the boundary curve, which is the circle of radius 3 in the xy plane. So that's r of t is equal to 3 cosine t in the counterclockwise direction. 3 sine t, and then z is just 0. 3 cosine t, 3 sine t, and then 0. So now let's calculate the line integral f dot dr. So this is, and this is 0 less than or equal to t, less than or equal to 2 pi. So 0 to 2 pi, f of r of t dot r prime of t dt, right? And what's r prime of t? Is 3 minus 3 sine t, 3 cosine t, 0. F is right here. F is z 2x 3y. So f of r of t, well, z is 0. 2x is 6 cosine t. And 3y is 9 sine t. So this is equal to the integral from 0 to 2 pi, f of r of t, 0, 6 cosine t, 9 sine of t, dot r prime of t, zero dt. So this dot product is 18 cosine squared t dt. Right? The product in the x-coordinates is 0. Product in the y-coordinates is 18 cosine squared t, and in the z-coordinates is 0. So this is equal to the integral from 0 to 2 pi, 9 times 1 plus cosine 2t dt. So this is 18 pi, and the integral of the cosine 2t from 0 to 2 pi is 0. Integral of the 9 is 9 times 2 pi, which is 18 pi. Right, and the integral of the cosine is 0. Because, we're going through 2 full wiggles of the cosine function. So the positive areas cancel out the negative areas. All right. So that's the calculation of the line integral directly. We could also calculate the surface integral. I'm not exactly sure what is it they're asking here. For the following exercises, without using Stokes' theorem, calculate directly both the surface integral curl of f dot ds and the line integral. So we did the line integral, right? So we did the line integral. We didn't use Stokes' theorem, because Stokes' theorem would give us the, so the same answer, if we did the surface integral. By the way, do you need to use that surface with Stokes' theorem? Which is the important thing in Stokes' theorem? Is it the boundary or the surface? Right? The line integral on the along the boundary is equal to the flux integral along the surface with that boundary. But what if two surfaces have the same boundary? Then what must be the case? What if two surfaces have the same boundary? What must be the case? Well, they're both equal to this. So they're both equal to each other. Right? So let's calculate. It says not to use Stokes' theorem. We might as well. I mean, we're on the subject, so we might as well do it. So let's actually now calculate curl of f dot ds. But let's not use s equal to the hemisphere. Or s equal to the hemisphere. Let's just use s equal to the disk in the xy plane. Has the same boundary. Has the same boundary. Right? Has the same boundary, so it's all good. This is fine because it's the boundary that matters, not the surface itself. It's the boundary of S that matters, not S itself. That's what, well, that's one of the things Stokes' theorem tells us. Okay, so the parameterization of the disk, x is x, y is y, z is 0. For the domain R, which is the disk of radius 3. Right, and then Rx cross Ry, well, Rx is I, Ry is J, so the cross product is I cross J, which is K, which is 0, 0, 1. Now, of course, you also have to do the curl. So F was, what was F? Blah, blah, blah. Is this. So F is equal to that. Now the curl of F is I, J, K, partial with respect to X, partial with respect to Y, partial with respect to Z. So in the X coordinate, it is 3 minus 2 is 1, right? This is 3 minus, no, 3 minus 0. This is 3, that's 2x. Derivative with respect to z is 0. In the j, you're going to have 0 minus 1, and then negate it, so you get 1. And in the k, you're going to have 2, which is 2. So 3, 1, 2. So that's the curl. 3, 1, 2. So the line integral over c of f dot dr is equal to, this is Stokes' theorem, curl of f dot ds, which is double integral over r, curl of f along rxy dot rx cross ry dA. Well, this is just the constant vector 3, 1, 2. Rx cross ry was just k. So it's the double integral of r of 2 dA, which is 2 times the area of r. Area of r is pi times r squared. So that's 2 times pi times 3 squared, right, which is 18 pi. Same answer. So now if you wanted to do the calculation over the hemisphere, using the hemisphere, I think that's going to be significantly more complicated because, gosh, the parameterization is going to be, it's going to have that square root business in there, 9 minus x squared minus y squared in here, if you're going to do the hemisphere. But somehow, in the end, it doesn't matter. Somehow, all that junk's going to cancel out and go away. And it's going to, turn into just, in the end, some simple little doohickey like that, double integral over r of 2. Or, I don't know, I mean, maybe like over here, you have some integral from 0 to 2 pi of cosine, which is just going to go away, be 0, or sine. Very neat how that all works out. Okay, 331. So f is equal to this. S is the portion of the paraboloid that is above the xy plane. So again, you can just take the disk, right? The portion of the paraboloid above, so this is just like that hemisphere, right? The portion of the paraboloid above the xy plane, so 331, similar sort of problem. So f is equal to 2y minus 6z 3x. And S is that paraboloid 4 minus x squared minus y squared. And when you get to the plane, the boundary of that guy on the plane, so this is 4 way up here, is going to be the circle of radius 2. Right, so that's the paraboloid. And of course it's going to be oriented in the outward or upward direction. Think. all boundaries are oriented clockwise and viewed from above. So now the boundary curve is going to be the positive orientation of this guy down here. Right? So again, C is just the circle of radius 2. So a parameterization is 2 cosine t, 2 sine t, 0. Circle of radius 2 in the xy plane. Right, so the line integral over c of f dot dr is equal to, well, and this is 0 less than or equal to t less than or equal to t less than or equal to 2 pi. So this is integral from 0 to 2 pi f of r of t. So x is cosine, so this is 4 cosine t. Y is sine, 2x minus, that should be a y. Nope. No. 2y minus 6z and 3x. All right, so 2 sine t, so that's going to be 4 sine of t. 6z is 0. And 3x is 6 cosine of t. Dot r prime of t minus 2 sine t, comma, cosine t, comma, 0 dt. So the dot product is minus 8 sine squared t, 0, 0. dt. Okay, so now using the double angle formula, it's minus 4 times integral from 0 to 2 pi, 1 minus cosine 2t dt. So this is just 2 pi, and again, the integral of that is 0. We're integrating cosine from 0 to 2 pi. Well, you're integrating cosine 2t from, so it's like integrating cosine theta from 0 to 4 pi. Right, and it's still 0. And so then this is 2 pi, so minus 8 pi. If you wanted to, so that's what it's asking you to do, is to like calculate that line integral, that vector line integral directly. Without using Stokes' theorem. But let's do Stokes' theorem. Which surface should I use? Should I use that paraboloid? I could. I mean, the paraboloid's probably less hurtful to use than the sphere because they don't have that square root to contend with. But what surface should I use? Again, it's the surface, not the surface that matters. It's the boundary of the surface that matters. As long as the boundary is C, the answer is going to be the same. Right? So I could take C to be the, to be the paraboloid or just the disk. And I'm going to get the same answer either way. But anyway, let's calculate the curl, and maybe we'll do it both ways. Let's see what the curl is. If the curl is just something really simple, then, well, we'll check it out. Okay, so now let's actually use Stokes' theorem. So that's F. So the curl of F is equal to y j k partial with respect to x, partial with respect to y, partial for the z, 2y minus 6z 3x equal to, so Partial with respect to y of that is 0. Partial with respect to z of this is 6. Minus 6, and you're subtracting it, so you got 6. 3 minus 0, negate it. Right. Now this is 0 minus 2. So that's the curl. Right, it's just a constant vector. So let's let S equal the disk in the xy plane. So Rxy is equal to, well, x is x, y is y, and z is 0. Right, where xy is the disk of radius 2. Like that. Right, so Rx, Ry, well, the partial derivative of r with respect to x is 1, 0, 0, that's I. For j is 0, 1, 0, that's k. So the upward orientation of this is the cross product of I then j, which is k, which is 0, 0, 1. So the line integral over c of f dot dr is equal to the surface integral over s curl of f dot ds. So it's a double integral over r. Curl of f is 6 minus 3 minus 2 dot 0, 0, 1 rx dot r cross ry dA. So it's the double integral over r of minus 2 dA, which is minus 2 times the area of r, which is 4 pi. Minus 2 times 4 pi. Right, pi times the radius squared, minus 8 pi. Same answer. Right, same answer, totally simple calculation. Let's actually do it with the paraboloid now. Let's calculate again. So calculate a third time. S is the paraboloid. So R, X, Y, X is X, Y is Y, and Z is 4 minus X squared minus Y squared. So partial derivative of R with respect to X is 1, 0, minus 2X. Partial derivative of R with respect to Y is 0, 1, minus 2Y. Rx cross Ry, I, J, K, 1, 0, minus 2x, 0, 1, minus 2y is equal to, so 2x in the x component. Oh, and the domain for x and y is again that circle of radius 2. It's the shadow cast by the surface in the xy plane, which is again just that disk. All right. So first this, yeah. So 0 minus 2x, positive 2x, and then here it's going to be minus 2y minus 0, and then you negate it, so that's 2y, and then here it's just 1. Okay. So the line integral over c of f dot dr is equal to the surface integral over s of the curl of f dot ds. Now, this step might be different from the previous one because the curl might have some, x, y, and z's in it, but the curl is the same. It's just a constant. So, because you got to take the curl along the surface, right? So it may be like x, y, z, x, y's, and z's inside this, in which case x is x, y is y, and z is fxy, which is 0 in this case. But down here, x is x, y is y, and z is this, right? But I mean none of that comes into the question here because the curl is just, what was it? 6, -3, -2 is just a constant. Dot 2x 2y 1 dA over r, where r is still that disk. So I've got 12x minus 6y minus 2 dA. Okay, so I mean, I've actually got an integration problem here. Well, it's over the disk. So now I'm going to transform to polar. Right, so it's 0 less than or equal to r less than or equal to 2, 0 less than or equal to theta less than or equal to 2 pi. So transforming to polar coordinates, 0 to 2, 0 to 2 pi, 12x is 12r cosine theta. 12y, or 6y, is 6r sine theta minus 2 r dr d theta. Right? I mean, non-trivial calculation here. Well, it's not hard, but it's not trivial is my point. So, what do we have here? 12r squared cosine of theta minus 6r squared sine of theta minus 2r dr d theta. All right, well, what's going to happen here? What's going to happen here? Maybe I should have done it d theta dr. So I'm going to integrate sine from 0 to 2 pi, and I'm going to integrate cosine from 0 to 2 pi. And what am I going to get both times? I mean, what's the sine look like? What's that integral? Zero, right? These are both 0. This one is just going to be 2 pi times that, so it's minus 4 pi integral from 0 to 2 dr. So minus 2, or there's supposed to be an r there, dr. So that's minus 2 pi r squared from 0 to 2 is minus 8 pi. Same answer. Same answer as before. Right, so, I mean, I did the, I did the integral, the surface integral of the curl, and the flux integral for the curl of f over the two different surfaces, but it didn't matter, right? You get the same answer both times. But, I mean, the calculation definitely looked a lot different. Right. I mean, in the end, this, the sines and cosines, they just integral from 0 to 2 pi is just 0. So they all just disappeared. Okay. So that was 331, 335, 339. 335. Use Stokes' theorem to evaluate that where C is the curve given by cosine t for x, sine t for y, and z is equal to sine t, traversed in the direction of increasing t. What would the surface be that satisfies that? Here it is. Hmm. Well, I think, unfortunately, that vector field is conservative. So, why are they? I don't understand. That's a nice problem, but the vector field is conservative. So in 335, so f is equal to. So notice that they give you the line integral over c p dx plus q dy plus r dz. So this is the vector field p q r dot d r. So where f is p q r, which in this problem is equal to 2xy squared z, 2x squared yz, and x squared y squared minus 2z, right, where c is something. They give you a curve. C is given by r of t equal to cosine t sine t cosine t, which is an interesting curve. It would be kind of interesting to do that problem. Finding the surface that works as a surface that has this curve as a boundary and all that nice stuff. Basically, um, this curve is the intersection of the cylinders. So like the vertical cylinder and the horizontal cylinder. That is so like x squared plus y squared is 1. So that's a cylinder. And then this one is y squared plus z squared equals 1. So if you take those two cylinders, that curve is the intersection of the two. Sort of the curve of intersection of those two cylinders. Not the whole thing, actually, just part of it. Because the whole thing is kind of like this X pattern. So it's just this oval pattern, essentially. Also, you have X equals Z. right? So it's the intersection of this cylinder, that cylinder, and the plane x equals z. Or so you could just take the cylinder x squared plus y squared equals 1 and the plane x equals z. So it's the intersection of that plane and the cylinder. But none of that junk matters. So it's this oval shaped thing. So that's C. But none of that matters because the curl of f is 0. So curl of f, I, j, k, partial with respect to x, y, and z, 2x y squared z, 2x squared y z, and x squared y squared minus 2z. So this is 2yx squared minus 2yx squared. This one is 2xy squared minus 2xy squared. So actually it's minus plus, but it doesn't matter, it's still 0. And the last coordinate is 2, so 4xyz minus 4xyz equals 0, 0, 0. So, so f is conservative. So the line integral over c of f dot dr is 0. Right? It's conservative, so you can find, you can find a potential function. The function has that as the gradient. So it's, what is it, x squared y squared z, I think, right? X squared y squared z minus z squared or something. Yeah. Actually, f x y z x squared y squared z minus z squared has the gradient of f equal to, I believe so, right? So the derivative with respect to x is 2x y squared z. Derivative with respect to y is 2x squared yz. Derivative with respect to z is x squared y squared minus 2z. Yeah. All right, so would be a nice problem to do otherwise, but that's what that one is, 335. 339. What did I do here? Oh, doesn't matter. So 339. Use Stokes' theorem to evaluate curl f dot ds, where f is that, and s is the half sphere. So the right half sphere. So x is equal to square root 1 minus y squared minus z squared, oriented towards the positive x, or not right half, but the front half, excuse me. The front half of the sphere oriented outwards, toward in the positive direction, the x-axis. So into our faces in the usual way we look at the x, y, and z axes. So again, you don't have to use that. It's not the surface that matters, it's the boundary that matters. So you might as well pick the disk. So for 339, so S is equal to, let me draw it first. All right, so you've got that oriented this way. So x is equal to the square root 1 minus y squared minus z squared. But, and the boundary is oriented that way to be positively oriented with regard to s here. But again, it's the because we're using the curl, right? Stokes' theorem applies. I mean, if we weren't talking about the curl, Stokes' theorem doesn't apply at all, right? I mean, if I'm just given a vector field f, so I'm just given some vector field f, and I'm asked to calculate the flux of f across this half sphere. Can I exchange the half sphere for the disk? No, I can't, because this vector field f is maybe not a curl vector. I mean, it might be, and I didn't know it, but it's not necessarily a curl type vector field. It doesn't have to be, right? But since we're talking about curls, it's not the surface that matters, it's the boundary that matters. Since, we're calculating to calculate the flux integral across S of the curl of f dot ds, which is equal to, via Stokes' theorem, the line integral on C of f dot dr. We might as well we can take S equal to the disk of radius 1 in the YZ plane. Right, this is the YZ axis. So we take RXY, RYZ, Y is Y, Z is Z, and X is 0. Right? It's a lot better than putting X equal to the half sphere. Or, you could use the paraboloid, right? So paraboloid, hyperboloid, whatever. As long as it's got the correct boundary, the surface is fine. So since we want to be oriented that way, RY, and towards the positive x-axis, using your right hand, curling in the direction from RY to RZ, right? Our fingers in RY to RZ. The thumb points, towards ourselves, so we're in the right direction there. So the partial derivative of r with respect to y is j cross the partial derivative of r with respect to z, which is k. J cross k is I, which is 1, 0, 0. Okay. The vector field f is equal to, well, some awful looking thing. E to the xy cosine z I have it written down. No, I don't have it written down here. Oh, here it goes. E to the xy cosine z, x squared z, and where did it go? X squared z, xy. Right, so the curl of f is, so e to the x, y, cosine z, x squared z, x, y, partial x, partial y, partial z, I, j, k. So this is equal to, so this one is x minus x squared. This one is going to be the negative of y minus this with respect to z, so plus e to the xy, sine of z, comma, k, so this is 2xz, minus this with respect to y, so it's x e to the xy cosine z. So again, pretty nasty looking. But, so this is curl of f. So curl of f along ryz is what? So this is the curl, and it's this ugly, yucky thing. So the curl along r of yz, x is 0, so that's 0. Y is y, and z is z. So this is minus y is y, x is 0. So that's e to the 0 is 1. And z is z. So that's just sine z. Comma, and then x is 0, so that jump's all just 0. So it's just y plus sine z negative. So the curl of f dot ds, where s, so this is equal to the double integral over r. Oh, and what's r? R is the disk. The disk of radius 1. So here's the y, z plane, and the domain for y and z is just that disk of radius 1. Alright, so that's r. Curl along here, so it's 0 minus y minus sine of z, 0 dot 1, 0, 0, ry dot rz, and it's just 1, 0, 0. So the whole thing is just 0. So this didn't matter. Let me just erase that. So it's a double integral over r of 0 dA, which is just 0. All right, so the curl is not 0. Okay, so that's not a conservative vector field. The conservative vector field, the curl is 0. It just happens to be that the flux across, across that surface is 0. Okay, so a lot of calculation, but no integral in the end. All right. So in the last few minutes, let us go to the section on divergence theorem, just so we can, get into that a little bit. We've talked about Stokes' theorem here. Let's take some time and talk about divergence theorem. I must have some notes on it somewhere. Okay, so next time we'll talk more about let's move on to about section 3.8. So let's go back to what was that last problem we did in section, the one with that cube there. Oops. So that was 305. So copy page. Oh, yeah, copy page. Paste page. Where's no, paste. Oops. So, well, it was number 305 here. So let's go back to number 305 in section 6.6. Okay, so in here we were asked, right, so calculate the vector flux F dot ds over these 5 faces of the cube. Okay, so via divergence theorem, says, whenever you have a closed, boundaryless, two-sided surface oriented outwardly, right, the flux integral F dot ds over S is equal to the triple integral over the inside of S. So R is the inside of S of the divergence of F dv. Okay, so here the answer to 305 was 3/4 for the 5 faces of the cube. Right, bottom face was excluded. Okay, so by the divergence theorem, okay, 3/4, which was equal to the double integral over S of F dot ds is equal to the surface integral over the whole cube F dot ds minus the double integral of the bottom face f dot ds, right? So we have the 5 faces, right? So let's just plop the 6 face back in there. So now I've got the whole cube, so a closed surface without any boundary. Right? But this one I can calculate via divergence theorem. Excuse me. Calculate this via the divergence theorem. Right? So the double integral f dot ds over the whole cube is equal to the triple integral of the divergence of f dv over the cube. Right? And what's the divergence of f? So f was equal to xyz, xyz, xyz. Right? So the divergence of f, right? So this is p, q, r. So the derivative of p with respect to x, derivative of q with respect to y, plus derivative r with respect to z. So this is yz plus xz plus xy. So it's the triple integral over the cube, right, of yz plus xz plus xy dv. So this is equal to the triple iterated integral 0, 1, 0, 1, 0, 1, yz plus xz plus xy dx, dy, dz, all going from 0, 1 to 0 to 1. So antiderivative with regard to x, so it's xyz plus 1/2 x squared z plus 1/2 x squared y. X equals 0 to x equals 1, dy, dz. So this is xy plus 1/2 y, 1/2 z plus 1/2 y, dy, dz. Antiderivative with regard to y, 1/2 xy squared plus 1/2 yz plus 1/4 y squared, y equals 0 to y equals 1. Oops, did I lose x, y, z? This is y, z, not x, y, y, z. Y, z, antiderivative with regard to y. I did this wrong. 1/2 y squared z. There we go. From 0 to 1. So this is integral from 0 to 1. So this is 1/2 z. Yeah, plus 1/2 z plus 1/4 dz. So this is equal to integral from 0 to 1, 1/4 z squared plus 1/4 z squared plus 1/4 z, I'm sorry, antiderivative is that z equals 0 to z equals 1. So that's 3/4. Right, so the integral on the bottom face is 0. As it should be, because, on the bottom face, z is equal to 0. So, on the bottom face, f x, y, z, which was equal to, f was equal to x, y, z, x, y, z, x, y, z, was equal to, well, becomes, because z is equal to 0, this becomes 0, 0, 0. So so the flux on the bottom face is 0. So the answer is 3/4. Right? So the flux over the whole cube, it's the same as the flux over the cube with the bottom popped out, all oriented outwards. Right? So divergence theorem, great. You know, made that a much easier calculation, because instead of 6 separate, of course you have to have a closed surface for divergence theorem. Okay, but when you do, you know, I mean, if we were to calculate that junk manually, you know, we'd have to calculate the vector flux integral over the 6 different sides of the cube. But here, it just turns the cube into one region over which to do the triple integral. Okay, so how about like 378? Divergence theorem. So fxyz is equal to this. S is the surface of the 5 faces of the unit cube. Why just 5? For the following exercises, use a computer algebraic and the divergence theorem to evaluate. Right, so probably on the bottom face, it's 0 or something like that. So let's check it out. So 378. So S is 5 faces of the cube, 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 1, 0 less than or z less than or equal to 1, excluding the bottom face. I think. No, it doesn't say. I think that's just a typo. It must be all 6. It must be all 6. It doesn't say missing the bottom. Is the surface of the 5 faces of the unit cube. It must mean 6. It's a typo there. So S is the 6 faces. Okay, oriented outwards. F is equal to, in 378, x squared plus y squared. What are they doing? X squared plus y squared minus x squared. So they just mean y squared? So I guess y squared, x squared y, three z. So the moral of the story is have a good set of proofreaders. All right, calculate f dot ds. So the flux from outside to inside of the unit cube over this vector field, which via the divergence theorem is the triple integral over the whole cube, right, the inside of the cube, inside in the boundary, of the divergence of f dv. Right. Well, this is f. The divergence of f, well, it's the partial derivative p with respect to x, partial derivative q with respect to y, partial derivative r with respect to z, where this is p, that's q, and that's r. So in this case, it's 0 plus x squared plus 3. Right? So this is the triple integral over the cube of x squared plus 3 dv. So that's equal to 0, 1, 0, 1, 0, 1, x squared plus 3, and I'm going to do dx, dy, dz. So double integral 0, 1, 0, 1, 1/3 x to the third plus 3x, x equals 0 to x equals 1, dy, dz, 0, 1, 0, 1. So this is 1/3 plus 3, which is 10/3, dy, dz. Right? That's just a constant. Integrated from 0 to 1, and then again from 0 to 1, so it just stays 10/3 both times. Okay? So I don't think they mean to the 5 faces of the cube, because they would have said which face was missing. I think they meant the whole cube. Actually, even on the bottom face, yeah, like on the bottom face, the bottom, if they meant the bottom face was missing, like z is equal to 0. No, so it's not 0. Oh, I don't know. I think it was a typo. Anyway, that's a reasonable example. Okay, so that's a few nice examples of Stokes' theorem and divergence theorem. We'll do some more examples of Stokes and divergence next time. And then what I'm going to do is go back to the beginning, and we'll look at the 8 types of questions that can be asked on such an exam. Okay, and we'll take the full 2.5 hours to do the exam, so probably I'll ask you to do all 8. Right? We'll have enough time to do all 8. I mean, it's 2 hours and 15 minutes. Okay, so that's all for tonight. And email me with questions and concerns. And if you need to meet with me, just let me know. Okay. Have a good night, everybody. See you on Monday.